All right, this is a review, follow-up on the review session we started Thursday and ran out of time in class. So we made it through, according to the stuff you need to know, or definitely need to know for the exam, the PowerPoint or PDF that's up on the website. For Prelim 1, we made it through the list of two things. We covered up through airfoil theory or two-dimensional lift theory, and we started in on 3D theory, and so that's where I'll begin now. So the idea is with a finite wing is that you have wing tips, and the wing tips are going to influence the velocity distribution around the wing. So we have some sort of wing flying through the air at some angle of attack, but it's a finite wing. And again, we have a low pressure on the upper surface, and we have higher pressure on the lower surface of the wing. If we view it from behind or from the front, it looks something like this, where we have low pressure on top. This is a very simplified view. High pressure on the bottom, and this induces velocity from the high to low pressure due to the pressure gradient from the lower surface to the upper surface of the wing, essentially leaking around the wing tips. So associated with that is a generation of a vortex. And due to our constraints from Kelvin's theorem about how vorticity works in the fluid, this vorticity streams downstream, and it's a bound vortex. It exists within the airfoil. And at steady state, we can consider it horseshoe shaped, but in reality there's a starting vortex of the that it leaves behind at the airport, but we can ignore that for now. This vortex induces a velocity, so you have flow moving around like this around the wing. Associated with that vorticity on the upper surface of the wing is a negative vertical component, and that is known as downwash. That is there because it is a finite wing and because it is producing lift. If it is a finite wing not producing lift, you will not have downwash. If it is an infinite wing, we do not have these wingtip vortices, and therefore we do not have downwash. So what are the consequences of this downwash? Well, let's just cut the wing somewhere. I'm just going to take a section of the wing, say right here, and we're going to look at that from the point of view of it as an airfoil moving through the air. So here's our flat motion. Something's going on with my pen here, one second. And we have an airfoil like this. Now, according to 2D theory, which I'll draw with blue here, we have our free stream flow coming in like this, and we have our lift being produced by this airfoil. It is normal to that flow, and according to inviscid flow theory, there is no drag on this wing. It produces a single force, which is a lifting force, which has no component in the direction of the free stream flow. Now, if we go add in our three-dimensional effects, we have this foil is experiencing a vertical velocity in addition to the incoming free stream velocity, and it looks something like this. That's probably a little bit large, but that's okay. It's good for this. It is good for this demonstration purposes. Let me just go back and add in what our effective 2D angle of attack was. It was here's our 2D angle of attack, alpha. Now we're adding in this induced velocity, this red induced velocity, which is downwash. So the resultant velocity vector looks something like this. It's experiencing flow coming straight head-on and flow, vertical flow, due to the downwash on the top of the wing. And so now this is our resultant flow vector, the flow vector experienced by the airfoil. So we have a reduced angle of attack. So we have initial airflow, looks like this, and we've moved it to something like this. And so now our angle of attack is much smaller. In this case it's somewhat exaggerated, but it's much smaller. It's moved from this whole part here to just this little part here is the angle of attack of the airfoil relative to the new free stream flow that it's experiencing right here. So we have a reduced angle of attack, which indicates that we need to be at an even higher angle of attack to maintain the same lift we would have if this was truly a two-dimensional airfoil. So reduced angle of attack, and we have because in 2D inviscid theory in general, the lift vector is normal to the flow direction, but our flow direction has tilted back, and therefore our lift vector, which I'll draw in red, has also tilted back according to this. So this is normal. This is 90 degrees to this line right here. So we have L primed and we have L. But drag, as we define it, is the component of the force parallel to the direction of travel of the wing, which is in the horizontal in this page. So this is going to be a positive drag force. This is what we want as a positive lift force, lifting it normal to the direction of travel. So note here, the direction of travel is not the same as the wind direction experienced by the 3D airfoil, which is coming slightly from above. So L primed is the net force vector generated in inviscid flow for this 3D wing, and L primed has some horizontal and some vertical components. So let me exaggerate it a bit more so it's clear. Here's an L primed, and we can decompose that into two forces. One is a true lift force normal to the direction of travel. One is a drag force in the direction of travel. So the main consequence of the 3D effects is a reduced effective angle of attack. So reduced alpha, which is going to have corresponding reduced lift. We'll look at the formula on the next slide. And we have a new drag component, which we're going to call induced drag. It is induced by the lift. Induced drag, or DI. DI exists because the airfoil is lifting. If it wasn't lifting, we would not have downwash. If we don't have downwash, then we don't tilt the lift vector and we don't produce induced drag. So it's induced by lift. It is an inviscid phenomena. It is not a it's not a viscous phenomena. It's an inviscid phenomena. But it's there, and we'll see how it depends on the lift. Obviously, it depends positively on the lift, but the exact relationship let's look at in the next slide. So this is really just a geometrical presentation. If you consider the effects of the wingtip vortices inducing a negative vertical velocity on the upper surface of the airfoil, which will affect the resulting inflow conditions to the airfoil, you can see how it's going to adjust the system of forces, creating a drag force that was not there prior in the 2D case or infinite span case, and reducing the lift from the 2D case. So the two formulas, which let me make sure I did put them in your sheet. It looks like I did. Yes, okay, so there's induced drag coefficient, CDI, is going to be equal to CL squared divided by pi aspect ratio. This is the induced drag on an elliptic foil. One of the consequences of Prandtl's theory, where he essentially used a distribution of horseshoe vortices to approximate the flow over a 3D wing, and then established the circulation. Well, basically, you can tinker around with the strength of the vortices, the span-wise strength of the vortices, to determine what the optimal lift distribution is. The optimal lift distribution is an elliptic distribution, so it's highest near the root and is weakest tailing off in an elliptic sense towards the wingtip. That produces a constant downwash. So elliptic lift. This is a lift distribution, so you can think about, here's your airfoil, and you essentially shape the airfoil either by twisting it, changing the section or changing the chord length so that you have the most amount of lift occurring at this section here and the minimum occurring out here, and the distribution ends up looking something like this. So you have lift occurring here, and it gets weaker and weaker, and it necessarily goes to 0 at the wingtips anyway. But how it goes, the shape of this is elliptical. And you can produce this if you use a constant twist airfoil, same sections. You can produce this by simply using an elliptic planform. So the chord varies elliptically, the lift will vary elliptically as well. This produces a constant downwash distribution that looks like this. Other lift distributions, any other lift distribution, will produce a non-constant downwash distribution. Maybe the downwash is stronger at the tips and weaker at the roots, as would be the case of a rectangular wing. Maybe it's stronger at the root and weaker at the tip, as would be the case of a triangular wing. Somewhere in the middle of a triangle and a rectangle is an ellipse, and that produces the optimal lift distribution. So this is the formula for that. You can see that the induced drag depends on the square of the lift coefficient. So essentially you're penalized by the square of lift. If there's no lift, you have no induced drag. The other key term in this is the aspect ratio, which tells us that the higher the aspect ratio is, the less induced drag you incur. And so essentially you're more closely approximating an infinite wing. We're taking the wingtip effect away from most of the airfoil by making it stretch far out to the sides. So that's where the aspect ratio comes in. A thin, long, thin wing is going to have less induced drag than a short, stubby wing. Even if they're producing the same lift, they will have different drags. And that is the reason that gliders and things that need to move efficiently, anything gliding is relying on its length or lift-to-drag ratio to maintain flight. And so the higher the lift-to-drag ratio, the better it will glide. And so you want a low drag to have a high lift to drag, and that is why you have long skinny wings on things like gliders. For a general airfoil, we can add an additional term here, E, and that accounts for geometric variations away from the elliptic. And so you had a homework problem associated with that, using a tapered wing, which is easier to construct, using the taper ratio to look up the E. So E will be less than 1 for an ellipse, E for anything less than that. So a tapered wing, which is a trapezoid, has a peak efficiency of about 0.95. For E, somewhere taper ratio something like 0.4, 0.35. So you can get pretty close to 100% efficiency even if you don't want to go and construct an expensive rounded wing. So that's the general formula for induced drag. And moving on to the effects on lift, and I did put the formula in. Okay, so the new slide here. For a 2D airfoil, we had CL equals 2 pi times alpha minus alpha naught. And again, alpha naught is the angle of attack for zero lift. So if you have a cambered wing, alpha naught will be a negative number. And this is essentially the linear part of the lift curve. So you have alpha, you have CL. At zero angle of attack, if it is camber, you will have some kind of positive lift here. In reality, the lift curve will suffer from stall at some point, but the inviscid theory does not account for that. So you're in this linear regime here. Thin foil theory says that lift curve slope is 2 pi for a 2D airfoil. So it's a nice way of very easily coming up with the lift slope for an airfoil. Of course, this doesn't take into account anything associated with the thickness of the airfoil and things like that, which will modify the lift curve slope slightly from 2 pi, but 2 pi is a good place to start. For 3D, we can write it, and there's two different variations of the 3D lift curve slope for thin airfoil. One of them is more suitable for higher aspect ratio wings. That is the one I will write for you now, and the form looks just like this: CL equals 2 pi times alpha minus alpha naught. And then we're going to divide this by a factor, which will be the three-dimensional effects. 1 plus 2 pi over pi aspect ratio. If we want to keep our little E factor in there, we can do that as well. So this is the new part. I'll box it in blue. This is the three-dimensional part here. And you can see that if aspect ratio goes to infinity, the quantity in that ratio goes to 0, and we return to the two-dimensional theory. If aspect ratio is finite, meaning we have a finite wing, we will produce lift, an effective lift curve slope, which I'll box in black, that is less than 2 pi, because the denominator is greater than 1. And so the result will be of a 3D wing will be just simply a lesser slope. So let's try to draw it like this. And that slope will depend on the aspect ratio. So here's 3 slopes. The 2D in red is the theoretical 2D solution, and then you have black of decreasing aspect ratio. So aspect ratio is going down in this case. So it affects your lift curve slope. And that is the effect of the induced angle of attack. And again, this is valid for high aspect ratio. Aspect ratio 1 or 2, there's another formula that you can use. But the type of foils we'll be looking at when we get into a yacht design and things like that, this would be okay. It's also good, okay cut. Let me just look at the stuff for the exam. Source of induced drag we discussed. Why does it depend on the lift? We discussed optimal planform shape, the elliptic, and I wrote technically the lift distribution because you're looking for an elliptic lift distribution. As I mentioned, you can make that by using twist and a non-elliptic planform. It is possible to do that. The examples I gave in class, the photos from some of the World War II fighters, those you can tell were elliptic wings. In fact, I'm looking at a photo of a B-17 on my wall, and it also has an elliptic wing. So quite a few low-speed planes had that. When you get to high-speed, transonic and supersonic flight, and Mach number effects come in, your issues change dramatically, and you start dealing with shock-related drags, and you typically see delta-style swept wings in that case, and you won't be looking for elliptical wings anymore. But for low-speed work, like we're dealing with, ellipse is okay. So that's about it for lift. But let's just think about what you would need to know to calculate, for example, induced drag on a wing. So we need to know the lift, and we need to know the aspect ratio, and possibly we need to know enough information to calculate E. So there's different charts for planform efficiency, and that can come from taper ratios, charts, and things like that. So essentially you have to find out what the geometry of your wing is. It could be a triangle, rectangular, it could be the example we worked in class was a pure taper, but in reality that Cessna 172 is a mix. It's a rectangular wing out to about half span, and then it becomes a tapered wing. So that's you would have to look up in a chart. But essentially those factors come together to give your induced drag, and then for CL, thus we need to know the angle of attack, geometric angle of attack. If it's a cambered wing, we need to know alpha naught. If it is a finite wing, we need to know the aspect ratio. If it's a non-elliptic wing, we need to know E, and that should be about it. To actually calculate the lift, now we're getting away from these lift coefficients, then you need to know the surface area, the velocity, and the fluid density. And that we can use to convert from CL to L and CD to D, or DI, I guess, the induced drag. We can add that induced drag on to what we've computed from the frictional drag, which we discussed on Thursday, to get the total drag on the wing. And of course, that's ignoring the third component of drag, which is viscous pressure drag or form drag, which occurs due to separation. Airfoils, by their nature, are very streamlined, and at reasonable angles of attack have fairly small pressure drags. It's when they start to stall or get a higher angle of attack that you have separation, and then the pressure drag becomes something to consider. But in reality, compared to bluff objects where pressure drag dominates, it is small when the airfoil is working in its reasonable regime compared to induced and frictional drags. The next thing is waves. I would like to talk about waves. Actually, I'm going to... a second here. Okay, I'm going to put that in a separate recording because I want to make sure this is working properly.